So my name is Lyublena, and I am here together with my colleague Mohamed, as you heard, to present to you a solution that we've been working on for the past couple of years at Datometry. And this is a solution that helps enterprises adopt cloud data warehousing technologies rapidly. But before we begin, I wanted to start with a quick quiz question. So analysts have estimated that enterprises over the next couple of years will spend about $60 billion. The question is on what?
Blockchain.
Good one.
Probably databases.
Well, the surprising answer is it's not databases. It's really replatforming existing applications to new databases. And if you think about it, this 60 billion number is larger than the size of the whole database market, which is estimated to be somewhere around 40 billion, I believe. Before we answer the question, why is that? Let's just first define what I mean by data warehouse replatforming. So here in this picture, there's an application which talks to an existing database. So usually that application connects over some protocol, which could be ODBC or JDBC, or a native protocol, and it issues queries to the database. And the database evaluates those queries and returns the result back to the application. And this could be any kind of application. You could think of business intelligent tools like Business Objects or Tableau or any of the other off-the-shelf tools developed for purchase or for licensing. It can also be an application that's developed in-house using some scripting language or Java or whatever higher level language. But the idea is that this application talks to the database, issues queries, and then processes the results back. So the problem of replatforming is when you want to replace the existing database with some new data warehousing technology, and we're seeing a big shift of enterprises wanting to move to the cloud for a variety of reasons. Mostly it's cost cutting, but it's also just ensuring future scalability and extensibility of the product. So there are three main steps if you want to take such an adventure of moving your applications to a new database technology. The first one is to move your database objects, and what is typically called schema conversion. So that involves translating all objects, including tables, including views, stored procedures, and so on, and moving those definitions over to the new database. It could involve details such as remapping data types if the two systems are not quite compatible in terms of what type systems they support. It could mean tuning the physical design if the new system doesn't give you the same type of indexes or partitioning or whatever knobs there are that you were used to in the old world. But that's kind of what this step involves. So once the definitions of the objects are moved, the next step is to actually move the data over to the new system. Sometimes it's a one-time thing if your data is static, but more often it's actually rewriting a variety of ETL scripts to pump data into the new system instead of into the old one. And the last step is application modification. So you need to make sure that your application can now talk to the new database. And that involves rewriting the queries such that they are understood by the new system, which typically speaks a different dialect of SQL than the one that those queries originally were written for. So now if you take these three steps and we project how much of these steps typically costs, you find it maybe surprising that the majority of the cost is not spent on the data migration and database migration, but actually on the application migration. So a lot of the times this takes up to more than 80% of the total cost of the migration project. And this is really kind of the nugget here, that migrating the database is not that hard. Migrating the application is the hard piece. And why is that? So in this chart, we ran a little experiment. So on the y-axis, we plotted a couple of features that we've seen, a SQL feature, that we've seen in various customer applications. And on the x-axis, we took four leading cloud databases, and we just counted how many of those databases support each of these features. So at the very top, you see the features that are very commonly supported. So these are very standard features like different types of joins, window functions, correlated subqueries, and so on. And most of the current database systems have pretty good support for them. But at the very bottom, you see that those are features that very few or nobody supports. And there's multiple reasons for that. It could be that these are harder to implement features and the cloud databases because they're still new and being developed. It could mean that they'll add those features in the next couple of years and you can take advantage of them. But more often it's actually proprietary features that nobody will implement because they were specific to that original database vendor that the application used to talk to. So if your application uses one of these features at the bottom, you kind of have a problem because those features will not work natively if you try to run them on a different database. And this is really what makes that whole step of migrating the application so expensive and so hard to do. Just to give you an example of what it looks like. So here we have a very small query that was shortened from a real customer query, modified to fit the screen. And the analytical queries are typically much longer. But even in that short query, there's already a few different constructs that make the query non-portable. So the first one is this keyword cell, which is just a shortcut for select. But it's something that the parser will usually give you an error for. The next one, if you look at it, it's a comparison, it's a filter of a date column with an integer. And the reason why this works in the original application is because the database vendor happens to represent dates as integers. So that's why they have a native comparison of date values to integer values. But that's not the case for the majority of databases out there. And there's some more. Here you have a subquery that compares a pair of values to a pair of values produced by the subquery, or the so-called vector subqueries. And these are also not standardly supported by the newcomers in the database space. There's a couple of more related window functions and very specific predicates. So as you can see, even this very little short query already has 6 different things that will likely make it not work on the new system when you try to migrate it. So this is where we come in to help with that problem. So here again we have the application that's talking to an existing database, as pictured in gray. And what you want to do is move that application you have to a new shiny blue database. And now the question is, how do you do that without having to spend a lot of money and a lot of effort in rewriting the application to be able to talk to the new database? So instead of rewriting, you put a virtualization layer in between. So this is what our product does. Our product implements an adaptive database virtualization technology, which intercepts the queries as they come in from the application. We translate the queries on the fly. We send them down to the system, and we know that we've translated them correctly and they are compatible in terms of syntax and semantics. And on the way back, we take the results and we translate them back to the same format that the application expects. So this effectively decouples the database, the application from the database, and you can run your application on a totally new database. So if you think about it, that's a little bit like VMware, but for databases. So instead of virtualizing the operating systems like VMware does, we are virtualizing the access to the database. And as a result, the application is no longer coupled with the data warehouse. And to tell you how we do that, I would like to welcome our chief architect, Mohamed.
Can you hear me? Okay, so what we do is basically the following. On your left-hand side, this is a typical picture, typical setup that your enterprise and customer have. Basically, you have existing applications designed to communicate and work with a particular database system using particular connectors. So these applications submit queries and requests using some wire protocol through the existing connectors. These requests go to the database, get processed, executed, and the results come back to the application. So this is the picture of setup before replatforming. After replatforming, the picture will look a little bit different. So your applications and connectors will remain intact, nothing will change there. And this is the main value proposition of Datometry. You don't, we have a solution that allows customers to move to new database technologies without touching the applications at all. So you still use the existing applications and existing connectors. However, instead of pointing directly to the database, you will point to our product, HyperQ. HyperQ will intercept the traffic coming from the application and rewrite the traffic on the fly, so that it fits the capabilities and expectations of a completely new database system. It could be on-premise database system, it could be in the cloud database system. We are not really restricted by that. So the application is still using the same wire protocol, the same way of communicating its requests as before. HyperQ, Datometry HyperQ intercepts that request, rewrite it on the fly into an equivalent request that the modern database system can process, get back the result from that database system, and again perform kind of the reverse translation. So reformat the results that come back from the new database system so that it fits the expectations of the application. So for example, we could map representation of different data values so that the application still receives the binary formats that it used to get. And as a result, the application is not changed at all. Probably the only change that you need to do in the application is just pointing the application to the Datometry HyperQ instead of the database system. Basically, a change of IP address or a small change in configuration. So how do we do that? So inside HyperQ, we have built a query transformation framework that is able to take an incoming SQL request and pass it through a pipeline of stages. And at the end, this incoming SQL query request is going to be translated into something that's equivalent to the incoming query, but expressed in the language of a completely different system. So in order to do that, we need first to understand the different constructs, that bits and pieces inside the SQL request. So this is where our parser component comes in. So we have different parsers that support different front-end systems. So you could have an application written for a particular database system. We have a parser component for that implements the grammar rules that has all the keywords, the syntactic analysis, like procedures needed in order to validate the correct syntax of the incoming query. As a result of that, we generate a structured representation of the query in the form of abstract syntax tree. Once we have converted the query from its free text form into this structured representation, we then go through the binding phase. And in this binding phase, we do more kind of involved operations, like looking up metadata, type derivation, and name resolution. So for example, your query might be accessing some tables, so we'd like to know what are the definitions of these tables, what are the data types that the columns inside these tables have, and so on. And as a result of that, we generate a richer representation of the query. We call it extra, stands for Extended Relational Algebra Expression. So this basically represents different logical operations inside your query. For example, here we know that this query is trying to do some sort of joins or aggregations or subquery, and there are correlations, and there are columns here, and there are constants there, and so on. So we have this extra as a language agnostic representation. It's kind of high-level representation of your query, but it's not really tied to a particular query language. It's in the form of relational algebra operators. This high-level representation of the query cannot be translated directly into SQL, so it needs to go through a phase what we call transformations. So these transformations now are kind of back-end specific. So we could here apply some transformation based on the knowledge that this query needs to be executed on a particular database system. These transformations do different forms of query rewrites, type enforcement, performance optimization. For example, we might shuffle operators around inside that extra tree. We might take one operator and split it into multiple operators. We might generate more extra expressions just because the backend system cannot handle the incoming request in one shot, and so on. So as a result of that, we generate this extra star, which is a more optimized, more fine-tuned representation of your query. At the last step, we take this extra star and then we serialize it. And serialization basically means converting that high-level query representation into some SQL dialects. So we generate SQL according to the keywords, according to the syntax rules, according to the formatting rules that the backend system supports, and generate this SQL out, which is an equivalent version of the incoming SQL expressed in the dialect of the language of the backend system. So the main principle of building this framework is extensibility. So it allows us to add, for example, different parser modules, different transformations, different serialization routines, so that we have the ability to extend the systems very easily by adding, for example, new transformations that implement certain rewrites, by adding new serialization routines that generate SQL in a particular way, and so on. So we have the ability right now to support, I think, around 6 or 7 backend systems, just because our framework is built in a modular way that allows us to extend it in a fairly easy fashion. So there are multiple classes of query rewrites we can perform inside HyperCube. The first class is what we call translation, and this is probably the simplest. So here we do things like syntactic mapping. For example, this keyword in the source language should be mapped to that keyword in the target language, or this built-in function name should be mapped to that built-in function name. So this is probably something that you may think I can even do it by writing a script that will just manipulate the SQL and generate an equivalent SQL. And you're probably right, because this is probably the easiest class of query writes that you need to do in order to migrate your queries. But things get a little bit hairy when you go to the next level. So here we have what we call transformation. So these are things that require you to understand the semantics of different constructs. It requires understanding of the holistic view of that query, and also the semantics of the source language and target language. Things like, for example, group by ordinal position, arithmetics on dates, implicit joins. You have now to understand how these features work in the source language, and if there are any equivalent features in the target language, and how to go from here to there. And this is where most of the time and money is usually spent. So typically this is solved right now by hiring someone who looks at your application and try to rewrite them manually. Very extensive process that requires lots of time, lots of money, and lots of testing. What we have is a software solution that tries to automate this process for you. Then the kind of the most difficult class, what we call emulation. Okay, so you can perform query rewrites as long as the target language has something that you can use. But what if the source application relies on something that's completely missing or lacking in the target system? So for example, things like stored procedures. Some of these cloud data warehouses does not have stored procedure support at all. So if your application logic relies on using stored procedures, you are now basically at a dead end. You cannot really migrate your applications to the new database system because it does not have the ability to support stored procedures. And in this class of rewrites, we can also help. So we provide what we call feature emulation. So things like stored procedures, for example, are unwrapped inside HyperCube and converted into smaller units of work that the backend system can understand. And these smaller units of work are sent to the backend system, and the results are stitched together so that the application still thinks it's using stored procedures, creating stored procedure, or calling stored procedure, even though the backend system does not have this support at all. HyperCube just does the unwrapping and monitoring of execution set of stored procedure to give the application the illusion that it actually is executing a stored procedure. And based on what we saw from our customer engagement, query writing is really purely syntactic, so it's never the first class. It's never possible to do it by just writing a script that will manipulate the SQL. You need deep understanding of the query constructs. You need manipulation of complex query structures. You also need to migrate missing features, things that used to work in the old system but are completely missing in the new system. So trying in the next couple of slides to give you more concrete examples. So let's look at this example, for instance. So here we are talking about a simple insert statement that tries to insert a couple of values into that sales table. And the schema of that sales table is composed of 3 columns, ID, amount, and sales date. And just because this particular database system supports date or represents date as integers, the sales date column here is defined as an integer. However, dates and integers in that system are implicitly converted to each other, which means you can insert a date value into an integer column, and that's perfectly fine. This insert statement seems to be ported as is, in terms of syntax, to new database systems. However, there's a hidden kind of bomb here, which is how are you gonna move this date value into an integer column. This is probably not supported natively by most other database systems. So we have some operation that tries to cast this date value into an integer in order to fit into that integer column. and we cannot really take this operation and serialize it and generate SQL out of it, just because it's not natively supported on the target system. So what we need to do now is to understand how dates are represented as integers inside the source database system, and try to produce SQL that will try to do the same in the target system. So it turns out to be something like that. So dates can be converted into integer using some formula, and this formula relies on extracting the different components of the date. So we need to find the year, month, day, and then plug them inside this computation in order to find the integer value that corresponds to that date. And if you want to translate that into SQL, you end up with something like this. You need to apply these extract functions, and then you apply these additions and multiplications and subtractions, and you end up with an integer value equivalent to the incoming date. So imagine that for this simple query, you would like to do something like that. You would like to replace each insertion of a date value into an integer column with this SQL snippet. Obviously, this is a tedious and error-prone job. So the framework that we provide automates this process. So whenever there is a task between a date and integer, this SQL snippet is going to be generated automatically. So obviously, this is a simple example. In the bigger scheme of things, you will find things more like complex, similar to this query. So this is the query that we saw a couple slides back, how it looks like in the source application on the left, and how it needs to be translated to work on a given cloud data warehouse on the right. So you can see here, for example, things like the keywords cell is translated into select. Comparisons between dates and integers need to generate this integer representation of the date in order to allow the comparison to work on the new system. Things like subquery that contains this vector semantics need to be translated into flat subquery and uses some existential quantifiers. And you need to push in this comparison inside the subquery so that the subquery still has the same semantics. Things like qualify or rank predicates. These need now to emit different SQL snippets, and the challenging part here is that this SQL snippet actually must be at different places in the query, so it's not even an in-place substitution. So you obviously need a principled framework that can understand the different structures inside your query and can generate this kind of translation in a principled way. So yeah, I think we move next to giving you some performance experiments, and then we can conclude.
So the first experiment I want to show is we wanted to see how complex customer workloads really are, because, I mean, you can take our word for granted that they are, but it's better to quantify this. So what we did was we took two example workloads from real customers, and those customers were from different verticals. And each one of them had a lot of queries to give. One had almost 40,000 queries for us to look at, and the other one gave us almost 200,000 queries. So what we did was we ran those queries through our product, and we just analyzed what kind of features each of these queries has. So to do that, we tracked 27 different features from the 3 classes we described before. So these were translation, which is the simple syntax-only remaps, the transformation, where you need to understand type semantics and you need to be able to reorder the query in a way that's compatible. And the last class was emulation, which meant features that don't have a native support in the target system and they need to be emulated in the mid-tier. So we tracked these 27 features, and in the first chart we measure what percentage of the queries were affected by some feature in one of these classes. When you look at the very bottom of the graph, you'll see that the second workload from the second customer actually needed a lot of emulation. So almost 80% of their queries relied on a feature that was not supported. And that feature was a form of stored procedure because they decided to wrap their business logic into stored procedures. So then every query was just calling the stored procedures with different arguments. And that's why you see this big number of queries affected by this problem. In the second customer, that was not the case, but they did have about a third of their queries affected by something that required a complex logical transformation on the query tree. And very few of the queries were really affected by something that was purely syntactic in nature.
Clarification? Those query counts, is that the number of SQL statements that appeared in their application code?
Yeah, so the question was, the query counts is that the number of queries, SQL queries appearing in the code. Yes, that was the number of queries that we saw.
Okay,
So basically, I asked them to give us a sample workload in order to tell them if we can support that workload or not. And that's what they came up with as a representative workload. The second example, we measure whether it's just one particular feature that their queries use, because whoever wrote those queries was a fan of that feature, or it's actually multiple of them. So again, we measured for each class how many of the features were present. And as you can see, it's never just one. So both customers used a third, which meant 3 out of 9 features we tracked that required emulation. And they, each of them had multiple multiple features from the transformation class. I think it was 7 or 8 for each of the customers that require deeper understanding of the queries. And if you were to hire somebody to do the manual rewrite, that person will have to look out for a lot of things. So it's not just one thing that needs to be taken care of, but it's multiple features that are complex in nature and need to be translated. So the second experiment we ran was we are a solution that sits between the application and the database. And a very common question is, well, do we introduce any overhead? And luckily the answer is no. So what we did here was we took one standard benchmark, TPCH, which contains analytical queries. And we measured 3 different things. One is the execution of the query on the target system. So this is the price you have to pay anyways, because you need to run your query against some system, whether it's the old or the new one. And then the 2 other components we measured was time that we take in order to support that virtualization. So the first one is how much time do we spend for query translation, and how much time do we spend on result conversion on the way back when the query completes. And this is the summary chart where I believe the overhead we introduced, which is this black and gray little piece of the donut, is not more than 3%. And most of the time is spent on actual execution in the target system. An overhead of 3 for an analytical application is something that everybody is willing to pay for.
How much was the execution time in these queries?
How much was the execution time?
Was it like for longer queries you would have a smaller effect, right? But for
right. So good point. So the question is how much time do these queries take, if we take short-running queries versus long-running queries, how much will this overhead change? So one thing that we should have probably mentioned is that we're focusing on analytical applications, because these tend to have very complex, long queries, and those queries typically take long time to execute. So we're not currently looking at transactional workloads where it's going to be sub-second, millisecond order of queries, but rather the larger queries. And part of it is because those queries are usually much more complex and much harder to translate. But yes, you're right that if we were taking sub-second queries, then probably the overhead would be bigger.
Can you make the case that your translation didn't make the algorithm of the query less efficient?
Good question. So if I understand correctly, the question was if our solution produced a suboptimal query translation. So this might be the case. Luckily, it's usually the opposite. It's usually we apply additional transformations to make the query run more optimally on the target system. Actually, yesterday we just did that exercise where we detected a pattern that the system was not handling well. So if you do the one-to-one translation, or the most naive way of translation, the target system was not handling it very well, whereas the original system was, and the customer saw performance degradation. So then we figured out what is an equivalent rewrite that makes the query run better in better time. And the good thing is that once we implement this rewrite, it applies to all queries that have this pattern, not just to the one you saw manually. Yeah, so the conclusion is that we saw from our experience is that we introduced a negligible performance overhead. So this brings us to the end of the talk. Hopefully we could convince you that replatforming is hard, but it's inevitable as more and more enterprises are looking to embrace cloud technologies, and that virtualization is a solution that helps you avoid costly and risky rewritings and delivers cost at a fraction of the time and risk that the old approach used to take. A little bit about us. We are about a 5-year-old company. We are based in San Francisco. There's a few of us here in the audience. Most of us are wearing the uniform, with t-shirts. We do have our product ready. We are already deploying it to customers. And we have open positions for developers of solution architects and more. So if you're interested, contact us, visit our website. This was actually an extended talk. We had a paper published in ACM Sigmund earlier this year. So check out the paper if you're interested to learn more details, or email us. Thank you.
So do you have any metrics of like what all source databases and destination databases you cover right now?
Yes, the question is what source and target databases we cover. So we, in terms of target databases, we support most of the modern databases out there, like Redshift, Azure, Postgres, Snowflake, a couple of others. Greenplum, yes. Source databases, we also do have support for some. We're working on adding more so that the solution is actually not limited, as Mohamed tried to convey. The solution is not limited to a certain pair of databases, but it can actually work for more. So we're working on adding more and more, and that's why we need engineers to help us get there.
I have a couple of questions, and one is similar to this question. So you have parsers that with custom queries, and like, do you have to do development, or as you said, there is cell instead of select and integer instead of date and all that. Do you have to do additional development to support the source application?
So the question is how much additional work is there in addition to the parser that we need to understand the syntax, if we need additional work to support the application. So typically no, so we're not a solution that works with some applications but not with others. Assuming that the application speaks well-formed SQL for particular dialect of SQL, then we can support it. And in terms of just how hard it is to add new features, we try to focus, for example, if you take the serializers, if you take the 6 databases that we support today on the back end, we assume that a lot of them will speak the core of SQL, which is the standard 2003 or whatever version of the SQL standard. So we try to produce queries that are very close to the standard way of expressing queries and not use too much of the syntax sugar stuff. So if we need to make an exception, if some system doesn't support a certain construct that is standard, we would implement it specially. But we try to keep it, the implementation concise so that
the other question that I have is, we are isolating the application from the data warehouse, and we are adding the queue in Hyperqueue as a middle layer and porting it to the cloud. So it can be not directly do one-time migration to the cloud to support the application in the cloud, and the application can still remain sticky with the data warehouse.
Yeah, so the question was whether we need this middle layer in between, or we can do a one-time migration and just use Hyperqueue as the tool to get there. So the short answer is no. And part of it is because a lot of the applications generate queries on the fly, so they might construct SQL statements out of some parameters that are passed to the application. So you don't always have the queries as one-time file of SQL queries. So they're oftentimes constructed dynamically on the fly. Not only that, but the objects that these queries touch can also be constructed on the fly. So we've seen a lot of applications that, for example, create temporary tables do some processing on those temp tables, and then go and produce the final result. So since you don't have the temp table definition when you translate the queries, you wouldn't be able to retrieve the metadata, you wouldn't be able to correctly identify what transformations need to kick in order to support that application.
Sometimes also the applications use tools that generate these queries, so you don't have access to the source of the queries. For example, it's a BI tool that your application is using, and based on some GUI actions, these queries get generated. So you don't have access to that source of the queries, just get generated under the hood. So there is no kind of static source that you can go and rewrite. You have to do that dynamically when the query comes in.
Thank you.
Yes.
The question I had is that do you do any many-to-many translation, or do you have some guidelines for what the source is and what's the appropriate backend? Because Postgres versus Redshift versus Snowflake, they're different behaviors and capabilities.
So the question is, if we do many-to-many translation, or we actually have recommendations. Do you want to take that?
Yeah, so actually one of the phases that we start with when planning for a project is give the customer insight on how it will look like if they migrate to a particular database system. So we have, as part of our product, something called query insights. And in this query insight phase, we basically analyze the workloads according to the capabilities of different target systems. And we give customers kind of scorecards that tell them, if you want to migrate to, let's say, Green Plum, we have, let's say, 90% of your queries supported, but the remaining 10% are not supported just because we still need to build new features, or maybe Green Plum is not that good for these features. But if you migrate to Microsoft Azure, for example, we have you covered all the way. So the customer gets this vision without executing any of the migration tasks. It's just kind of offline, static analysis of the query workloads that tells them if they migrate to a particular systems, what do they expect? What should they expect?
So you're actually profiling the workload over a period of time,
Exactly.
and then give them the guidance.
Exactly. Yeah.
How does the software get deployed? Is it the library, or is it the server somewhere, or how does that work?
The question is, how do we deploy the software?
So the software can be deployed either on-premise or on the cloud. It's basically a binary that sits between the application and the database. So it's a very lightweight binary that you can basically just extract and copy, put it on a VM in the cloud, put it on a machine in the on-premise data center, or wherever you like. So you don't have any restrictions around where the product is deployed, as long as there is connectivity between the application and the place where the product is stored, and connectivity also between that place and the target database. This is only required.
So there isn't a lot of requirement in terms of CPU or memory or whatever it is that the translation requires?
Yeah, so they take quick translations very lightweight on CPU. Probably we see more CPU consumption when we do result conversion, and there we have some tricks. So for example, we can bump up the parallelism so that we can perform the result conversion a little bit quicker, but at the cost of consuming more CPU. But in terms of query translation, it's very lightweight on CPU.
If you have access to the source of the application, do you compare the performance difference?
To compare performance difference, you have the source. The question is, why would you want to do that? If the customer there's different reasons why customers want to move away from a database vendor. And performance could be one of them, but oftentimes we see that it's actually things like scalability and cost cutting. So if the customer is interested in comparing the performance, they can actually do that, because they can run the query or their application against the original database, and without spending much money and time on porting their application over, they can use us as the middle layer to actually run those queries against the new system as well. And they can do that side-by-side comparison if that's something that interests them. So we are enabling, we are not doing it for.
Yeah, and good thing also about cloud data warehouses, many of the performance problems can go away by just beefing up your setup on the cloud. So for example, adding more compute node, increasing disk space, increasing memory on the machine when you run your database instance. This can take care of some of the performance problems. In our POCs, we run performance experiments where customers, for example, have SLAs that tell us that these jobs, for example, have to execute within this number of hours. And after using the Datometry hypercube, we monitor the execution time and see if this execution time fits the SLA, then we're good. Otherwise, we either need to beef up the cloud instance that we're using so that the queries run faster, or we can also implement like job-specific transformation that helps the optimization. So these are some tricks where, for example, we can improve the performance of some queries by orders of magnitude just by manipulating the SQL in a way that fits the capabilities and features of the cloud data warehouse.
Any more questions? Okay. Let's thank you to the speakers.